Quantum mechanics, how incredible it is. Your phone, something that you probably love the most. Today, computers and phones would not have existed without the application and discovery of quantum mechanics. Now, think about the computer that uses the very nature of quantum states for calculations. Machines that are up to billions of times faster. Nations looking at it as a kind of weapon, and from Twitter to TikTok, people can't stop talking about it. But as we push toward scalable quantum computers, decoherence remains a critical challenge. Traditional error correction methods rely on redundant qubits and complex pulse sequences, adding overhead that limits scalability. This leads me to my central research question: how can we empower qubits so that they could internally cancel their own noise? To answer this, I needed to determine if self-correction is physically possible and if it can be integrated into superconducting qubits without the baggage of external error correction apparatus. Hence, Pico experiments show that a precisely timed 180-degree pulse can reverse dephasing, which shows that error need not to be permanent. Given the right stimulus, they can be reversed. Alongside this, dynamic decoupling uses control pulses to continuously smear out noise. Inspired by these mechanisms, I developed quantum eco-pairing architecture. This idea includes error correction within the qubit itself using a novel twist: internal self-coupling mechanism. Think of it as a built-in self-correcting mechanism similar to negative feedback loop in classical electronics. In our design, an one-chip tunable coupler is integrated directly into each qubit circuit. Acting as a built-in undo button, this coupler feeds a controlled portion of the qubit signal back into itself to counteract phase errors. Following this, we apply precisely engineered time reversal microphase pulses to create internal echo, effectively reversing the buildup of phase errors. Let's see how we validate KEPA with our targeted experimental approach. First, precision pulse generation. Using cryogenic pulse generator, we create highly controlled signals through squid-based Fox modulation, which will ensure precise error correction. Second, qubit fabrication with built-in correction. So each qubit is electro-beamed pattern with an integrated tunable coupler, allowing it to self-correct errors dynamically. Third, ultra-cold operation. We keep qubits at 10 millikelvin in a dilution refrigerator, minimizing noise to ensure maximum coherence. Moving ahead, we aim to scale KEPA to multi-qubit systems addressing crosstalk with machine learning calibration. And we integrate KEPA to topological and spin qubits so that we develop universal error suppression strategies. Most notably, I want to investigate intra-qubit self-coupling within the bulk sphere by engineering targeted interactions that force each qubit to automatic transition to a lower energy state, a state significantly below the ones that are reached through decoherence and environmental coupling, so that it naturally remains in internally stabilized configuration. Thanks for your attention.